We have metals on the product table, right? I think I said this last time already, but when you look at the product table right here, right, the periodic table has this line, right, this little stair-stepping line right there, and that line there actually separates the metals from the non-metals. Everything from here to the left is metals. Everything from here to the right is non-metals, right? But then everything that's on the line, the stair step, is what we call a metalloid. So it acts like a metal, but it's kind of like a non-metal. It's kind of in between, right? So just so you know, when you add the word oid or when you add the suffix oid to the end of anything, it means that it's not exactly that, but it's like that. So, for example, if we ever encounter aliens, right? We know that they're not, and they look like people, but we know they're aliens. We call them humanoid, right? Because they're not exactly humans, but they look like humans, so they're humanoid, but they're aliens, right? The same thing with metals. Okay, metals, they act like metals, but they're not exactly metals, so they're called metalloids. So everything on the stair step is a metalloid. Okay, everything on the stair step is metalloid. At least all the ones you care about that are on there are metalloid, right? So some properties of metals, right? Metals, just obviously, right? They're very shiny looking, right? They conduct heat and electricity, and they're solid, right? They're all solid. But the only thing that's not a metal is, that's not, sorry, the only metal that's not a solid is mercury, which I think I told you the story. Did I tell you the story about me playing with the mercury and almost, getting contaminated? I didn't tell you about that? Oh my God, it was crazy. So I'm working in my lab, and I have three classes, so I can't remember the stories I tell to everybody. I'm working in my lab, and in the incubator there's a mercury thermometer. Okay, and so I reach into the incubator and I pull out something and I knock over the thermometer. It shatters on the ground, and all this mercury just flies everywhere. It just rolls all over the floor. And if you've never played with mercury before, you can actually gather it up and pick it up and play it with your hands. It's it's almost like metal putty, and then you can like do this with it. And at the time, I didn't know it was toxic, but it turns out mercury is toxic. So it's a that just shows you, you don't really know your chemistry till you get out of school. So while you're in school, it's like, it's fine playing with mercury, it causes you to go crazy and stuff like that. Um, like the phrase "Mad Hatter," that comes from like going crazy from mercury poisoning. If you didn't know that, from like Alice in Wonderland, Mad Hatter. Um, Not specifically diethyl mercury, but it's still close enough. Anyway, so I'm playing with the mercury. I'm like, oh, this is so cool, and I'm just like letting it drop in my hand like putty. And my boss comes in and he's like, "What are you doing? What are you doing?" I'm like, "Oh, I just dropped a mercury thermometer, and I thought it'd be fun to play with it." And he goes, "Oh my God, we have to call hazmat." And so they called hazmat, which really sucks because it was the it was the weekend right before. It was a Friday right before Labor Day weekend, so they were pissed off that they got called in. And they come in, and here I am playing with the mercury still. And they come in their hazmat suits, and they start shooting like sulfur everywhere, just like all over the place, because sulfur will attach itself to the mercury, and it makes it easier to sweep up. You can sweep it up. And I'm standing there. I'm like, "Do you guys need me to do anything? Like, should I go somewhere? I mean, And then because they're all in their suits, right? And like, oh no, 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 you're fine. You've already been contaminated. There's really nothing we can do for you. So we'll just clean up the mess and we'll see you later." So I'm like, all right, well, here's the mercury. So I handed them and they didn't take it. They made me put it into this jar. Well, yeah, that was kind of funny the way they did that. So word of wisdom: don't play with mercury.
At least do it with gloves on.
Yeah, that works too. That works too. Oh, that's not as bad as some professors I've known. Like I had a one boss. He would, if he ever saw something on a table like a powder or a liquid, he'd just like touch it and then he'd taste it and he'd go, oh, it's acetic acid. Oh, that's sodium bicarbonate. So I don't think you should be tasting that stuff. He's like, no, it's fine. Death is in the dosage, which is actually true, by the way. Death is in the dosage. So I'm not the worst. Then we have the nonmetals. Okay. Then we have the nonmetals. They're on the right side of the product table. They include hydrogen. So hydrogen up here is on the left side of the product table. So it's the only one that's on the left side that is not a metal, right? Because it's a nonmetal, but it's on the left side over here because it's got one electron, right? That's the reason why. So there's always exceptions to rules, and hydrogen is one of those exceptions. So hydrogen is definitely a nonmetal, right? But you know that nonmetals like carbon, bromine, is a liquid at room temperature. There's neon, right? That's a gas at room temperature. So the point of this line here is to show you that nonmetals can exist in all different phases of matter, right? Solid, liquid, and gas, right? But metals can only really exist as solids, right? At room temperature, at normal temperature, you know? So except for mercury. So that's really what it is there. So there's bromine right here, right? Bromine is a brown gas. Chlorine is kind of like a green gas. Carbon powder. Oh, I should have brought my fingerprint powder. That's all carbon powder. We could have done fingerprints today. It would have been fun. Phosphorus. There's sulfur. See, that's what they had this. They had these like guns that like shot sulfur everywhere. So it's like a yellow powder. It's kind of interesting that way. Very interesting. So now we talk about the metalloids, right? They're the ones on the step stools, right? So elements on the step stool line are called metalloids. The only ones that are not metalloids are aluminum, right? Which is that one right there. See, it's not the color. It's the ones that are purple, right? So, or pink or whatever, lavender. Who knows what color that is? But aluminum is not a metalloid. I don't even know what PO is, but that's not a metalloid. And AT, I forget what AT is too. So that's not a metalloid. Anybody know? If you don't know, it's fine. Huh? Antimony? It might be. Hey, good on you. You're right. So, good on you. See, just because you have a PhD in chemistry doesn't mean you have to memorize the periodic table, just so you know. And I will never make you memorize the periodic table. Okay. Some profs do though. I had a prof when I was going through school that was like the first exam was, fill in the first 20 elements of the periodic table, and then the next exam was fill in the next 20 elements. All through the semester was fill in the next, I'm like, oh my God, we get the periodic table everywhere we go. Why do we need to do this? Right? What a waste of time. Anyway, so.
Maybe at least you got 20 questions.
Yeah, if you've remembered it. I mean, that's a lot of stuff to memorize. All right. Which the following is not a metalloid? B, right, which is boron, right? So you even have to look at it to see. Silicone, aluminum, or technetium. You're wondering to yourself, how does he not know what AT is, but he knows what TE is? So, but yes, TE is technetium. All right, let's see how you guys answer this question. Oh, man. Yeah, I'll never make you memorize unless you want that. I mean, because that does, if you're a good memorizer, it's good for extra points. Yeah. It's fine. Do you see how long it took me to sign in just now? And I work here. You'd think it'd be better than that. Every time? What is it asking you? Which one is it asking you? What's the question it's asking you? Oh, no, I guess I could scan it to see. Oh my God. What? Why is this happening? Why is this happening? Why is this happening to me? Did it say, did it? Oh, why is this happening to me now? Oh yeah, you're right. It's actually answering that one. Let me see real quick and make sure. Does it say which of the following is the alkaline metal? Yes, it is. Well, you can keep on answering it. That's fine. Go ahead. I can see here how everything's going anyway. So we'll just add on to that one. I must have messed up the QR code, Yes.
It'll be the first time you've ever had everybody completely wrong in your class.
Right. Actually, in forensics yesterday, I had 3 in a row that everybody got right, which never happens either. So that's crazy. It's absolutely crazy. All right, so just make sure you scan in. You scan in for that one, and because it tells me the date that you did it too. So yeah, just answer it for attendance purposes. Did you know that they're actually requiring faculty to drop you from the class if you have more than, for a 2-day class, 2-day week class, you're only allowed to have 3 absences, I think. And if you miss 3 days without telling me that you missed 3 days, I am actually required to drop you now. It's crazy. That's never been like that before. No, I mean, and the thing is, like, it used to be our choice to do it. I used to just let people, hey, if you don't want to show up, but you do great on the test, good for you, man. But they're actually requiring professors to drop you if you've missed more than 3 days, unexcused. It's crazy. It's absolute crazy. Well, so now that we're face to face, you've got to show up here. All right. Okay, so let's see here. Yeah. Well, that's excused though. That's true. That's true. That's very true. Yeah. It's again. I know. I mean, it's against my pay. I mean, sorry, it's above my pay grade. But, but yeah, I have no idea. I disagree with that policy. Right. So I only got 10 people. Is that only 10 people in here? 4, bad at math. 7. We're missing 1 person. Who hasn't done it yet? Oh, okay. Okay, well, that's fine then. All right, so the answer here, which since I messed it up. I messed up the barcode that was on there. The answer here is aluminum. I just said that, right? Aluminum is the only one that's not a metalloid. I am sorry about that. QR codes look all the same, man. They really do. So, oh man. Oh, I forgot to mention this. You guys have lab today, right? Make sure you have your notebooks because the school bookstore does have those notebooks that Ms. Dickens requires. They do have them, and if you don't have your notebook, you will get a 0 for the lab. Like, you have to do that. Okay, there's no it's stupid that we have to use this notebook. There's no that one right there that Courtney has right there. You have to use that notebook because if you don't, you will get a 0. That's what it needs to be. It needs to be a carbon copy notebook. You cannot just make a photocopy of your notebook and then give us the copies. It has to be carbon copy, right? And it's just one of those things that we require. And think of it like this: I don't require you to buy a textbook, right? So, and that textbook's like $200. So use that extra money that I have allowed you not to buy a textbook, right, to get yourself a carbon copy notebook. Do not go to the lab today without a carbon copy notebook. All right. I do not want you to, because understand that if you don't do lab the way they tell you to do lab, they will give me a 0 for your lab, right? And that's 25% of the grade in this class. You will not get higher than a 75 if you get perfect on everything in here if you don't do the lab correctly, right? So I'm just warning you now. All right. So make sure you have time right after class, go get a notebook. All right. So chemical formulas, right? Chemical formulas. The subscript to the right of the symbol of an element tells the number of atoms on each element of the molecule in the compound, which we talked about that before. So when we see things like this, remember that hydrogen here. So there's a whole bunch of elements that are called diatomics. And what that means is that they cannot exist just as a single atom. They've got to be together with another atom of themselves, right? They have to be with themselves. And so hydrogen is one of them. Hydrogen is an atom that cannot be just an H by itself. There's got to be 2 of them together. Same thing with oxygen. Oxygen is the same way too. You always see oxygen as O2. You never see it just as O, right? And so these are all called diatomics. There are a few more of them. Chlorine is that way as well. Chlorine like that. Fluorine is like that. Helium is like that too, right? And so this number right here at the bottom right-hand corner, what we call the subscript, it tells you how many atoms are in there, right? So I talked about water before. Water here is actually H2O, right? So there's 2 hydrogens there and 1 oxygen. That makes water. Here's hydrogen peroxide, almost exactly the same thing as water, except it's got an extra oxygen, right? So hydrogen peroxide is a super strong oxidizer. I don't know if you were kids, your parents would, feel like, if you got a cut or something like that, you'd have to, they just pour hydrogen peroxide all over it, like it was a good thing. So it does. I mean, it kills things, but it also kills you too, right? It kills your cells. You wonder what that bubbling is happening. That's all the bubbling that's occurring is the hydrogen peroxide is actually destroying, exploding your blood cells, right? So it doesn't just kill bacteria, it also kills you too. Not you personally, but like your cells. So, I mean, I guess it's a good thing if in hindsight, needs of the many type of thing, but, be careful with the hydrogen peroxide stuff. So molecular compounds, right, are generally compounds that only contain nonmetals, right? And we'll talk about this later in the semester, but molecular compounds are also known as covalent compounds. They share electrons, right? So carbon monoxide, right, is definitely a molecular compound. It's got one carbon, one oxygen, and then carbon dioxide is carbon with two oxygens. So carbon monoxide, mono means one in Greek, right? So that's why it's carbon monoxide, one oxygen, and then carbon dioxide, right, has two oxygens. So di means two in Greek, right? So those are some of the things you're gonna have to remember. Mono means one, like monocycle, monocle. Some people think I look good with a monocle. With a single glass up there. Like the Monopoly man. Or who's the guy with the peanuts? Anyway, di means two, right? Like diabolical. No, that doesn't make sense. Di just means two. Remember that. Huh? Di what? Yeah, no, that doesn't work either because that's two. Oh, dichotomy. That works because dichotomy means to split two ways. Dichotomy, right? So di means two, and then tri is easy. Tri is three. Then four is tetra, right? And then you'll get to the rest later. But anyway, those are the ones that you got to memorize, right? Anybody ever seen anybody with carbon monoxide poisoning before? It's pretty bad. Did I ever tell you the case about that case where have I ever told you anything about a carbon monoxide forensic case? I have. Okay, then you already know. So I won't tell you that story again. Where the guy got chopped off the guy's, in half, the lady in half, threw the bottom half in the river. I told you about that? Okay, just make sure. You want me to tell the story again? Okay. uh, anyway, carbon monoxide. And then we have these organic chemicals too. So when you get to organic chemistry, they have their own nomenclature. Meth means one carbon. Eth means two carbons, right? And Eth means two carbons because Eth is the same thing as ethanol, right? Right, where you're drinking alcohol is called ethanol, and it has two carbons in it, right? And then three is actually prop, and then four is bute, like butanol or butane. Butane, yes, exactly, butane, yes. So that's got four carbons, right? So we'll go through very deeply on how to name those molecular formulas later, but those are all molecular compounds. And just remember that molecular compounds are only compounds that contain nonmetals, okay? Those are molecular. I talked about this just a second ago, right? We have these things called diatomics. Hydrogen is a diatomic. Nitrogen is a diatomic. Oxygen is a diatomic. Fluorine, chlorine, bromine, and iodine. So just memorize these. Make sure that you know whenever you see any of these that they can only exist as two of them together, okay? Okay? Just remember that. It's an easy thing to remember, okay? So there's a couple types of formulas. There's called the empirical formula and then the molecular formula. The empirical formula gives you the lowest whole number ratio of each atom in the element of a compound, right? And then the molecular formula gives you the exact number of atoms, okay? So I don't really find the empirical formula super helpful because it's more important to me to know exactly how many atoms are of each in the compound, right? But just know that there's an empirical formula and then there is a molecular formula. So for you to be able to think about this logically, what does it mean to be an empirical versus a molecular? Let's go back to talking about hydrogen peroxide, okay? Whoops, wrong way. You see hydrogen peroxide right here, right? It's H2O2, right? That would be known as the molecular formula. because it tells you that there's 2 oxygens and there's 2 hydrogens. The empirical formula would just be HO, right? Because that's the lowest common denominator, lowest common multiple, whatever it said, right? And so let's do the same thing again with methane then, or ethylene rather, right? Ethylene is C2H2, but C2H4, right? C2H4. So that would be its molecular formula. What would its empirical formula be? Exactly, CH2, right? That's the difference between an empirical formula and a molecular formula. You need to know what both means, but the vast majority of time you will get it in molecular formula, right? Exactly what the molecule is. Because what's the use of knowing that that's one carbon and two hydrogens when it's supposed to be 2 carbons and 4 hydrogens, right? So just know the difference between the two, but know that the vast majority of the time we will give you the formula in the molecular way. Okay.
I guess it would tell you like the ratio.
Yeah, if you're trying to do that, that is true. That is true. Oopsies. All right. So if we know the molecular formula of a compound, we can determine its empirical formula. The converse is not true. Okay. So there are a few ways we show molecules, right? Here's the molecular formula right here, where all you see is just the carbon and the hydrogen and how many hydrogens there are for methane, right? That's methane. So this is called the structural formula, where you actually draw out how many carbons there are, or sorry, you draw out the carbon and you actually draw out how many hydrogens there are, and then you put them around the carbon, right? So 4 hydrogens on 1 carbon. Carbon is the center atom because there's only one of them, right? And so the hydrogens go around it, right? This is called a perspective drawing, but more specifically what this is in organic chemistry, we call it a line angle drawing, right? In organic chemistry, we call it a line angle drawing. And what it's doing here is it actually shows you that the carbon is not just a flat thing on the piece of paper, but it's 3-dimensional, right? So the bond angles between carbon and the hydrogens here are 109 degrees, okay? 109 degrees. And so to make it so, and you'll learn about this later on in life too, it's the VSEPR theory. We'll talk about that later. But it's trying to maximize the position of where the hydrogens are so that they're the furthest apart from each other, right? They're the furthest apart from each other. And so this is what we call a tetrahedral. This shape is called a tetrahedral. And so when it's a straight line like this right here, a straight line like that, that means that the hydrogen is in the plane of the paper, right? It's flat in the plane of the paper, okay? When you have a wedge that's dark, like a solid wedge, dark, that means it's going out towards you. It's pointing towards you, right? So this hydrogen right here is pointed out towards us, okay? And then a dashed wedge is when the hydrogen is in the back and pointing towards the back of the paper. Does that make sense? Right? So I know the hardest thing about chemistry is seeing chemicals and molecules 3-dimensionally, right? And so it's easier to see them if you have a molecular model kit, right? But we don't have one with us right now, so we'll figure that out later. So then you have the ball and stick model, which you can see the ball and stick model, right? Notice how these 2 hydrogens right here. So by the way, carbon is always black, hydrogen is always white. The carbon's in the center here, right? And notice this hydrogen right here is going up and down. So it's flat in the plane of the paper. This hydrogen right here is also flat in the plane of the paper, right? But notice that the one with the solid wedge here is coming out towards you, right? And the one that's dashed wedge is in the back going towards the paper. Does that make sense? Right? The hardest thing about chemistry is the 3-dimensional stuff, okay? To me, at least, it was the hardest. Oh, and I forget about the math. There's a lot of math too, but we'll get to that later, okay? And then we have the space filling model. I rarely ever see things in the space filling model, but it's the same thing as this, except there's no sticks, right? Because these sticks represent bonds, by the way. If you didn't know that, the sticks right here, those all represent bonds, single bonds to be exact. All those lines, those are all single bonds, okay? Any questions about the 3-dimensional picture of an atom? Nope. Good. So, which one of these is a diatomic? Let's hopefully it scans the right place now. It goes to the right. What am I saying? Does it? Good. Yes, it does, because you guys are already answering. Is there something I can help you with? Something wrong? It should come up pretty easily, I thought. Yeah, I got you. That makes sense. But yeah, you guys need to take, Gen Chem 2. Take it with me in the summer. It's a good time. It's really like, it's every single day. But that's how it is in the summer class. I might just get as tired as you. Everybody answered? I only got 9 people, so there should be 12, I think. No, 10, 11. God, I always forget. 2, 4, 11. There should be 11. So 2 more people need to respond. And I think Chris already did his, so 2 more people need to respond. Yes, Chris already did his. Do you need me to call on you to tell you that you haven't done it yet? Okay. One more person. All right, everybody's in. I'm going to actually show you this one because it answered the correct question, right? 2 people answered A. I don't even remember what A is, but that doesn't matter because the correct answer was D. It was all the above. So good job. Most of the class got that one correct because hydrogen is definitely a diatomic. Oxygen is also diatomic. Nitrogen is also diatomic. So that's definitely all the above is the correct answer. So good job. There might be a question like that on the exam, so make sure you get that clear. Okay. So let's talk about ions now. So we've talked already before about what happens when you change the number of protons. What happens? Yes, you change the element. Exactly. You change the number of protons, you change the element, correct? Okay. So what happens when you change the number of neutrons? Exactly. You change the isotope, right? You get a different isotope. So now let's talk about changing the number of electrons. Okay. So changing the number of electrons, right? Here, when an atom of a group of atoms loses or gains electrons, what does it become? It's called an ion. Okay. Okay, so you need to know that. Okay. Changing protons changes the identity of the element. Changing neutrons changes the isotope. Changing the number of electrons changes what? Makes it a different ion, changes the ion, okay? And so I was already telling you about this before, right? Because I like to skip ahead for some reason, right? But the group number, right, tells you how many electrons there are in the what? Valence shell, the outer shell of electrons, correct? Right? So it also tells you then what kind of charge it has, which then tells you what ion it is, okay? So for example, we'll take a look at fluorine right here, right? It's in group 7, right? It's in group 7. How many electrons does it need to get to 8? All right. What? 1, exactly. It just needs 1 electron to get to 8, right? And so, since it needs 1 electron to get to 8, when it gains that electron, right, it's no longer neutral. What is its charge? It's -1, right? And so that's called the fluoride ion. Does that make sense? The fluoride ion. Same thing happens with chloride, bromide, iodide. All of those do the same thing. How do you know this? Because it's in group 7, right? And group 7, if you subtract it from 8, you get 1. Now that's a charge of -1, right? And that's how you know that it is an ion of charge -1. So everything over here, all the nonmetals, right? All the nonmetals are going to be what? Negatively charged, right? Why are they always negatively charged? It's because they always have to gain an electron, right? Does that make sense? And so since they're always gaining an electron or 2 electrons or 3 electrons, they're going to be a negative charge, right? So group 7 is always -1, right? Group 6 is always -2. Holy cannoli. 6 plus 2 is what? 8, right? Group 5 is going to be -3. 3 plus 5 is what? 8. Does that make sense? We're all trying to get to 8 here. Does that make sense? So all these over here are going to be negatively charged, okay? And based on the group number, you can subtract it from 8, and it gives you the charge it's supposed to be. Does that make sense? Okay? So let's talk about the metals now. The metals. If nonmetals are always gaining electrons, what do nonmetals do? They give them up. And when you give up an electron, what charge do you become? Positive, right? So sodium, right? It's going to give up how many electrons? Give up how many electrons? 1. So what is this charge going to be? +1. Let's move over to his neighbor, magnesium. How many electrons can it give up? 2. What is this charge? +2. Get it? Right? So the sodium ion, right? And see the fun thing about the metals, you don't even have to subtract it from anything, right? The group number just tells you. Okay? So the group number is group 1 for sodium, for lithium, for potassium. All those, they lose 1 electron. That's its charge, +1. Then magnesium, beryllium, calcium, strontium, all those in group 2, also +2 charge. Makes sense? And most commonly, what's going to happen is that you're going to have nonmetals want to, like I was saying before, like chlorine is so insidious, it would just steal an electron from sodium. But sodium is like, just take it. I don't care, right? And so it's like one of those, what's yours is yours and what's mine is yours too. Is that right? No, what's no, what is my girlfriend always says, what's mine is mine and what's yours is also mine. That like that. So anything that I own, she also owns, right? But anything she owns is only she owns, that kind of thing. So chlorine is like that, right? Chlorine is like that, right? I think I need to rethink this actually. No, I'm just kidding. But anyway, so chlorine, right? I'm sorry, nonmetals, right, are always going to combine with metals, right? And that's what we call ionic compounds, right? Before we had molecular compounds, right? When it's 2 nonmetals put together, those are called molecular compounds. But then when you have a metal and a nonmetal put together, right, in that kind of give-take relationship, right, not really sharing, that's called an ionic compound, right? So vocabulary words you need to know. If it's a metal and it's losing an electron, it's called a cation, right? When it's a nonmetal and it gains electrons, it's called an anion, right? Cation and anion, all right? You can see how the periodic table tells you everything you need to know about these elements, right? If you know how to read the periodic table, this is your best cheat sheet ever, okay? And like I said before, you always get a copy of it. You always get a copy of it for everything, okay? So the only thing that doesn't fit in with this rule is what? It's the noble gases, right? Because they all already have 8 electrons. So they don't care, right? Have your fun. Do your little menage a trois. But I already have my 8, so I don't need to combine with anybody else. So some common cations, right? We already talked about these before. We've got hydrogen here, lithium here, sodium. Notice that the plus sign right there, right? All those tell you what the charge is, right? All those tell you what the charge is. All these are +1 charge because they're also in what group? They're group 1, right? And they are alkali metals, right? So the one that's not is the silver ion right here, right? And the silver ion is in this group here called the transition metals, right? And there's silver right there, Ag, right? The thing about the transition metals is that they can have multiple charges. So sometimes you have to say things like silver 1, silver 2, silver 3. And that tells us what the charge is going to be, right? I'll show you how to figure out what the charge is in a second, right? But just know that if it comes from the center part, 3 to 12 right here, if it comes from 3 to 12, it's a transition metal, right? It's a transition metal, and it's possible that it can have more than 1 charge, right? And I'll show you how to figure that out in a second. All right, so And if you ever wondered, why is it that this part of the product table is set lower than the rest? That's the reason why, right? Because these transition metals act differently than the other ones do. And so they're set separately from the rest because they have special rules, okay? So, you're taking your test and I say, what is the formula for iron 3 oxide, right? You're like, okay, wait a second. I have iron. I have oxide, oxygen's right there. But crap. Oh no. Iron's in here, right there. It's inside the middle of the transition metals. I can't just do the easy old, figure out it from, 1 and 2 just from the group number, right? You've got to actually go through a process. And I'll show you what that process in a second, right? We also have these other ones here. Here's the ammonium ion, right? It's actually a nitrogen with 4 hydrogens. You know what ammonium is? It's literally Windex, right? You use it to clean windows, right? That's what ammonium is. And then copper. Copper is the same thing as silver. It can have multiple. It can have like +1. It could be +2, +3. It just depends. And we'll talk about how to figure those out in a second. Or I don't know if it's going to be today, but we will talk about it later, right? So, some more ions, some more cations. See magnesium right here, right? Magnesium, potassium, strontium, barium, they're all right here in the second group, or the alkali earth metals. What is their charge? Their charge is 2. Zinc, though, zinc here has a +2 charge, but notice zinc is right there, part of the transition metal, right? So zinc can also have more than 1 charge. So don't just trust that it's always going to be 2, right? We have cobalt here. That's a transition metal. Copper, iron. Notice, remember we had back here, we had copper, right? Oops. We had copper right here, right, as a charge 1, right? But then we also have copper here as what? Charge 2, right? So there's iron there, manganese, mercury, nickel, lead, right? Did I tell you guys about lead already? How Pablo Escobar used to be like, do you want lead or do you want not platinum, silver? And he would say plomo, right? And that meant lead. That's where that comes from, right? Crazy Pablo Escobar, right? I lost my train of thought. Anyway, did you know actually that cocaine is not like a narcotic? Did I tell you that already? Yeah, cocaine is not a narcotic. It's actually a stimulant, right? But for some reason, like the DEA and all the government calls it narcotics, and so that's why the show on Netflix is called Narcos. Really, the show should be called Stimulantos, because that's what cocaine is. Cocaine is actually a stimulant. So I would call it Stimulantos, but I guess it doesn't have the same ring to it as Narcos does, right? Because if you didn't know this, narcotics are actually things that kill pain, right? They're all painkillers. And let me just tell you, I don't know from experience, but let me just tell you, cocaine does not kill pain. Okay, it kind of amps you up. Okay, so it's definitely not a narcotic. It's a stimulant. Well, that's a completely different, like, mechanism there. Not the same kind of mechanism as it would be as yeah, we'll talk about that later. Oh, you're not in my friend's class. We won't talk about it later. But anyway, it's like Jurassic Park. Like most of the animals and the dinosaurs in Jurassic Park are actually from the Cretaceous period, right? But they named it Jurassic Park. None of those dinosaurs are from the Jurassic period. They're all from the Cretaceous period. But Cretaceous Park doesn't sound the same, I guess. It doesn't sound as good. So they named it Jurassic Park. So I don't know what that means, but anyway. So you have plenty of metals here that have multiple charges, and that's what I'm showing you there. Okay, so here's the ones. Here's some anions now. Luckily for you, the anions all have the same charge, right? They, only have 1 charge. You don't have to worry about those, right? So not iron. Hydrogen can also hydride. Hydride is an ion that has a -1 charge. Fluoride, -1 charge. You already knew that. Chlorine, bromine, iodine. This is cyanide right here. That's got a -1 charge. This is hydroxide, which is a base, a super strong base. If you ever had one of those carnival pretzels, the big ones that you dip in cheese, they actually use sodium hydroxide lye to actually set the dough for that, right? Good stuff there. But they use it for something. I don't know if it's about setting the dough. I just made that up. But they use it for some step in making pretzels. I'm not a chef. How would I know, right? Acetate ion. This is from acetic acid right here. Chlorate, perchlorate. Oh my gosh, what is going on here? It's my mom. It's like that commercial. It's like that insurance commercial, right? Like your mom calls at the worst times, right? And the guy's like fighting off like spies and terrorists or something, and he's on his phone with his mom. He's like doing a high kick. You're calling at the wrong time, you know. And your mom's like, hey, do you know where I put my shoes? So I'm like, no, I don't know where you put your shoes, mom. Killing me. Anyway, so all these have -1 charges. These right here that have more than one atom are called the polyatomics, right? They're called the polyatomics. And I'm sad to say this, I'm sorry about this, but you're going to have to memorize the polyatomics, okay? There'll be a list of them coming up soon, and you'll have to memorize this. All right, so more polyatomics here. Chromate, carbonate right here, sulfate. Sulfate makes sulfuric acid. Phosphate makes phosphoric acid, right? All those things. Oh, nitrogen. So these are all have 3 charge. Nitrogen has 3 charge. We talked about that a second ago. Sulfur here, oxygen. So good stuff. But yeah, you're not gonna be able to figure out that. You could, if you wanted to, go through the periodic table and count up the charges for carbon, count up the charges for oxygen, and then do the math to figure out the exact number of charge that would be there. But for me, it's just easier to memorize it because there's not that many of them, right? It's faster to just memorize. All right. So, which of the following then is an anion? Which of the following is an anion? My mom was probably calling to ask me if I had bought her Ford stock yet. I'm like, Mom, I'm not your investment banker. But for some reason, she feels like I need to. No, right? I don't know. It was hard enough to explain to her what Ford was. So I take that back. Mom knows what Ford is. But still. Why do I get so sweaty teaching this class? It's like I just get too excited, I guess. Too excited. But this morning when I got to the campus, it was like one of those days where it was like cold, but not too cold. So you feel like you need to have your core warm, but your arms aren't, so you don't know what to wear, Really? We're gonna have another freeze? What about the low? I need the low to be a little bit lower. Because right now it's 66 degrees outside. So, all right, still waiting for 2 people. Oh, so it's actually going to be kind of warm compared to it was last week. All right, so 10 people have answered. I'm still waiting on the last person. Oh, there it is. The last person just came in. Let's see here. So, vast majority of you answered B, which is indeed correct. It is not D because look back at the thingy here. Right, ferrous is definitely a cation because it's a metal, right? And then cupric is a cation because it's a metal, right? Because remember, cupric is from copper, ferrous is from iron, right? But the nitride is the only one that's from the right side of the periodic table, right? So you have to be on the right side of the periodic table to actually be an anion. Okay, good stuff there. Good stuff. So here are the polyatomics, right? Not all of them, but just to talk about them, right? Sometimes a group of atoms will gain or lose electrons, and these are all the polyatomics, right? So here's a polyatomic, which is ammonium, NH4. It's got a +1 charge. Sulfate, SO4, right? It has a -2 charge. There's a few of them you have to memorize, but those are all called polyatomics. Okay. And then, so after we get that, we can put it together with this thing that we call I see I jumped ahead like I always say, right? There's these things called ionic compounds, right? And they're generally formed between a metal and a nonmetal. And so sodium chloride, right, is a ionic compound, right? And in ionic compounds, like I said before, electrons are transferred from a metal to a nonmetal, right? So sodium here actually gives up its extra electron and gives it to chlorine, right? And so when that happens, see here's that electron right there. That extra electron goes to chlorine, right? That turns chlorine into the chloride ion, and then that makes sodium the sodium ion, right? So notice that the only thing that gets the "ide" at the end is what? The nonmetals, right? You only get the "ide" if you're an anion, right? The sodium or the metal stays the same. Okay. So here's a very explosive sodium atom, right? Expose it to water, it just blows on you. Okay. And then here's the chlorine atom, right? You breathe it in and you choke out, right? But then you put it together, right? And you transfer one electron from sodium to chlorine, making the chloride ion, and then you get this thing here, a crystal structure of sodium and chloride ions, and that crystal structure is salt. It's the same salt that you always use, right? Same salt that you always use to salt your steak, right? The same salt that's in your body right now. Okay. So let's talk about how to name these. Talk about how to name these now, right? So we talked about this a second too, right? Not a second, a while back too, right? So say we take something like magnesium, right, which is in group 2, right? And since it's in group 2, it's got a positive 2 charge. And then we take something like nitrogen, which is in group 5. What is group 5's charge? What is group 5's charge? -3, right? -3. So how do we write a formula so that both magnesium and nitrogen can be together, right? And make it the molecule neutral, make the compound neutral, right? Because nature wants things to be neutral, not charged, right? And so all you really have to do is, hey, there's a 2 here and there's a 3 here, right? All you have to do is then move the 2 for the magnesium and put it there for the subscript for nitrogen, and then move the 3 for the nitrogen, and then make that the subscript for magnesium, right? And the reason why you can do that is this, because if you make a 3 here and you multiply it times 2, what do you get? 6. And then if you take the 2 here and you multiply it times -3, what do you get? -6, right? -6 plus +6 is what? 0, and it's neutral now. So the goal whenever you're writing these compounds right here, whenever you're writing these ionic compounds, the goal is to have the compound end up being neutral in charge. Make sense? Right? So just like I was saying before, sodium is +1, chlorine is -1. You put it together, and what's your charge? 0, right? Make sense? Water, right? Water is so oxygen, right? One oxygen, which is -2, right? And then you have two hydrogens. What's the charge on hydrogen? +1. So 2 hydrogens is +2, and then one oxygen is -2. Put them together, what do you get? 0, right? That's how you write these compounds. Your goal in writing ionic compounds is to make it so that the subscripts will always make you end up with a 0 charge. Make sense? And it's as easy as just moving the charge from one place over here, right? From there to there, and that to that, right? So the charge of the metal becomes the subscript for the nonmetal, right? And then the charge of the nonmetal, or the anion, right, becomes the subscript for what? The metal, right? Is that confusing? Does that make sense? Okay. All right, good stuff. All right, so let's see where we are. Okay, there we go. So here's your next thing right here. I was going to end the class soon, but we still got a couple minutes left. Ionic compounds consist of which of the following? A metal and a metal, a metal and a nonmetal, a nonmetal and a metal, or none of the above? Let's see how you answer this. You know what? I think I'm just going to end the class there, actually, after you answer this question. give you a little bit of a break until you have lab. That will give you time to go get a notebook if you don't have one. So I'm serious. I'm just trying to be. I just want you to be successful. I really do. Right. And I don't have any control over the grade that you get in lab. Right. And if they give me a 0 because you didn't have a notebook, that's really going to suck for you, and I'm not going to be able to do anything about it. Oh, huh? Oh, in order. So it should be like an order, right? Is it a metal and then a non-metal, or is it not non-metal first and then metal? Does that make sense? When you're reading the formula, is it a metal and a non-metal, or is it a metal and a non-metal? Yes, ma'am. Yes, that's it. That's the exam material will end with what we ended today. Yes. There will be nothing from the exam on the exam that's going to be from Monday's material. Okay. That would just be douchebaggery, wouldn't it? Give you an exam the same day that I just taught it to you? I mean, I'm a douchebag, but not that big of a douchebag, huh? You think it would be? Yeah. Uh-huh. So you're really behind with the exam, but you're super ahead with the lecture. That sucks. Sucks. It's never going to be like that here. Like, so yeah, I would have actually preferred to have it where we had the discussion first, and then had the exam. I mean, we could do that. Do you want to have the exam first and then have lecture? Would that be better? Because the time in the exam, sorry, the time that we have in class and the time that we have in discussion is the same amount of time. It's 1 hour and 15 minutes, right? So if you want to have the exam first in class, like in here, and then in discussion we have the lecture for the week, right? We can do that. Do you want to do that, or would you rather have the lecture first and then have the exam? You want to do it that way? I can do whatever the way you want it to do, as long as you show up for discussion. If I do that, you better show up for discussion. Don't just go home after the exam. Okay? I will be very upset if you don't show up after discussion. And you don't want to make me upset. Okay? All right, we'll do that then. We'll have the exam first, and then we'll have our lecture that day. So before you leave, let's take a look at the distribution, right? The answer here, most people answered B, right? And that is correct, because in an ionic compound, we always have the non-metal first and then a metal. Wait, sorry, a metal first and a non-metal. I read that wrong. Sorry.